Now we have our flattened feature map that is giving us this as the number of inputs, number of query vectors, and this will be the corresponding positional memory. Suppose this was the original data. What will happen is this is our input, right, to the hidden layer. So then if it was the original detection transformer, there will be a query matrix that will take this input and produces the query, and there will be a key uh, transformation layer which will be a linear layer that will take this and produce the key, and then we will be doing a qk transpose by this, and this will be the normal self attention, right? uh, so what the problem here is, this dimension is the problem, so this will be a high computational cost. So now we want a mechanism through which we can actually attend to a smaller layer. So we don't want to attend each query to attend to each other query. We want each query to attend to a set of other queries, not all this. So how, what deformable attention is solving is how can each query attend to a set of other queries. For that, what they do is, like each they introduce a sparse attention mechanism where each query attends to a small fixed number of query sampling points or other query vectors across each different level. So what we want is each query to attend to some features in each feature level. So suppose what we want is, suppose so essentially each query is from a layer, right, a linear layer. So what we want is each query to attend to one point here, some point here, some point here, and some point here. So this is what we want our query. And initially we know, if we know the query's position, we can actually correspondingly look into the corresponding position in other feature maps. So suppose if we are looking into the top first feature map, and we can correspondingly look into the corresponding points in the other feature map. Suppose if I'm looking into the point 0. 0.5 0.5 in this feature map, a coordinate, then I can correspondingly look in the corresponding 0.5 here, 0.5 here, 0.5 here. But that might not be so this we can set it as an initial a reference point from which we can make the network learn which points to look into. So this is the next thing we need to know. So initially we can say that for a corresponding point we need to look into the corresponding other points in other feature maps. That is one thing we can do. So for one point, say we look into four other feature points in four other feature maps, so that will give us a 4.42 matrix. But there is one another problem here. So this is first of all a hand woven feature. So we want to make somehow the network give us the input to where to look into. So what we do is we will have a feed forward network that predicts us the, so we have xy's, right? So we want a network to give us some delta x delta y's. So we want a feed forward network to give us the delta x delta y's. So suppose if we know the points, corresponding points in each feature layer. Now we want a feed forward network so that the network can actually learn to attend to different features to give us the delta x delta y. And we say that we want the network to give us 4 delta x delta y's across each level. So what will happen is now we have each point in each layer. So for each point in each layer we want the network to give us 4 delta x delta y's, right? So that we can add to these points and get the corresponding 4 other locations. So 4 other locations across each feature map that we can attend to. So what we are telling is, so we have a query, right? We have a query queue, and we want the network to give us, to predict delta x delta y across four different feature map. So it's basically predicting how many points, four different points across four different feature map. That is predicting 16 delta x delta y's. That is 60 predict synchronous 2 points. They are delta x delta y's, and add to the corresponding query, so that query or the reference point of the query, so that we get the corresponding points to look in. So we know the position of the query. So suppose this is the first position, we know the x coordinate of the query, or the xy coordinate of the query, because it basically comes from a feature map, and we can actually look into the corresponding points here in other feature map. And this is possible because all feature maps are normalized to 0 1. And then we have a feed forward layer that predicts us 4 points per layer, such that the delta x delta y per layer is possible. So we have a feed forward layer that predicts us 16 points, 16 delta x delta y, such that uh, each point in each point can give us four different delta x delta y's. So now we have a feed forward layer helping us find 16 other keys to look into. But we also want to learn how much weightage each of these keys should have. So what we have is, we have another feed forward layer. So we have one feed forward layer that is giving us 16 delta x delta y. We have another feed forward layer that gives us 16 weights of this 16 delta x delta y. So we have basically, instead of a q projection matrix and key projection matrix, what we have is two sampling, a feed forward layer that gives us the sampling offset, and a feed forward layer that gives us the attention weights. So that is what I have written here. So what we have is a feed forward layer that gives us the sampling prediction and attention prediction, instead of the query projection and key projection. So basically these will be kind of replacement for the query projection and key projection in the normal self attention. The value projection will be same. There will be a it will happen similar to what's happening in the uh, self attention. So the next point is, once we have these points, we need something called bilinear interpolation to actually get the points. So what I mean by that is, so what I mean by bilinear interpolation is, suppose the network by so we have our reference points, and our network gives us the delta x delta y, and we added the x plus delta and y plus delta y. So this need not fall into the center of a coordinate. So we might not actually get the center coordinate from the feature layer. So suppose this can actually come here, right? So this need not fall into the center. So this is some grid, I'm assuming. So this need not fall into the center of the grid. It can fall into some position like this. So what bilinear interpolation does is, it looks into the 4 points across it, and does a weighted average of these points based on the xy. So suppose if this is f1 f2 f3 and f4, and this is our point of interest, what the final f will be, some weighted average of all these points. And what the weight will be, it will be the how much delta x and how much delta y distance each center pixel is from it. So this will be delta x1 delta y1, this will be delta x2, there will be delta y2. These are actually the how much is the offset of each of the point from this point. And this will be delta x3 delta y3, and this will be delta x4 delta y4. So similarly, for all those points, we do this bilinear interpolation and get this point. So what happens is, in essentially, so we have per layer 4 points, and each of these 4 points is actually looking into four other points through bilinear interpolation, right? Even though in the end we are having 4 points per layer, each of these 4 points are looking into four other points via bilinear interpolation. So this bilinear interpolation is a totally differentiable function, so the gradients will flow easily back through these points. So essentially, even though we are saying we are looking into 16 points, each of these uh, 16 points across all the four layers, each of the 16 points actually is coming from a bilinear interpolation of 4 points. So essentially we are looking into 16 to 4 points, but this, yeah, the other 4 points are implicit, not explicit, in the sense they come from a bilinear interpolation and not directly into it. So that is what we say here when we mean by, so sample points are fractional, so bilinear interpolation is used to extract these points from the map, and finally we multiply the attention weights to get this uh, how much each of the points correspond weight corresponds. So in the paper they explain it with a neat diagram. So here, as I said, they have a query. From the query they predicts the delta x, delta y's, which they add to a known say query. They know the position of the query, right? Because the query comes from a feature point, they know the xy's of the query. They add the delta x, delta y to that query matrix, and they also, from the corresponding query matrix, they get the corresponding weightage of each of them, and they sum it up, weight it up, and finally they get the one weighted matrix out of like it's in after that it's correspondingly a dot product extension, right? You have say four queries or 16 queries across all 16 keys across each or 16 queries across all the four layers, and the query attends to those 16 features, and we get multiply by the corresponding weights, and we get the corresponding output in the end. So this is what's happening. So now I will look into the implementation details of what we just discussed. So initially what we need is reference points of each queries. So each query is having a reference point. So each query is from a feature map. So we actually can get the reference point from each of the feature map. So what we need is the reference point of each query is actually the center point of each, say, reference map. So if you have a 134 coin 134, what we need is the center point of each reference map, and we want it in a 0 to 1 normalized coordinate system, so that we can correspondingly look into, say, if you say 0 0.5 or this whatever this point is, we want to look into a corresponding point in the next feature map. And if it's only possible if you normalize it into 0 0.0 to 1. So how we do it in PyTorch is, so we have a torch.linspace command, and here we are saying start from 0 0.5, which is this end, to here into the height minus zero point 0.5, and similarly for width, similarly we want to start at the center, end at the center, and then we normalize with the corresponding height and width so that it becomes in the 0 1, and then we stack them as xy coordinates so that they become reference point. So this will give us the reference point in one say one feature level. So we want the corresponding point across four different feature level. So what we do is we just do an expand across initially we expand across the batch, so that the same feature is across different batch, and then we have to also expand along uh, uh, along the L, which is the feature level. So number of levels is 4 here. So that the same point corresponds to we want the same. So if I am looking into this point, the center point, I want to look into the corresponding center point in the other feature levels as well. So sorry for the poor drawing, but yeah, that's what we intend to do. So this is done here. If you want a bit more clarified representation or explanation, I have a small note. Yeah, so what's happening here is here we have this is the what mesh grid output. Say suppose we are going through 67 into 67, so what mesh grid give will be, this will be starting from 0 0.5, this will be ending in 66.5. Similarly across all the rows it will be repeating, y0 to yn will be repeating across the rows So here it will be starting and it will be ending in 67, and this will be repeating along all the say here across all columns and here across all rows. And then we reshape and we divide by height, so it become in the normalized coordinate 0 to 1. So we do that here as well. We reshape it and we do weight divide by w, so it becomes 0 to 1. And then we stack them, so x0 it become x0 y0 x1 y0 xn y0, then x0 y1 x1 y1 xn n1, finally xn yn. So we get the center point of each of the reference point. Now in a0 to 1 normalized coordinates, then what happens is, as I said, we do the batch level expansion and then we do the feature level expansion. So finally we have h comma w is the flattened level, this much reference point per feature level, and we have to do it for all the feature levels. So we have to initially do it for 134 into 134, then we have to do it for 67 into 67, then 34 into 34, and 17 into 17. So you have to do this for all the feature level and finally stack them all together. Yeah, so once we do it for all the feature level and stack them together, what we get is the same number of queries for all the queries. We get xy point, and since we are doing it across 4 different levels, we get for for xy is for 4 different levels and 4 different batches. So that is what we get after the first so now we have the reference point. The next thing that we need is, we need to predict the delta x delta y's, and we need a network to predict the delta x delta y's. So here what we actually use is a simple linear layer. So we want it to take in the query vector whose dimension is embedding dimension, and we want it to predict how many points. We want it to predict 4 points per how many levels? 4 levels. Each point have 2 coordinates. The other thing is, since this is a multi-head attention, we want it to predict it across 8 different heads. Say suppose if you are using 8 n number of heads in this example, I'm using 8. So you want the network to predict 8 different heads, the delta x delta y is across 8 different heads. And similarly, you want another network to predict the corresponding weights of those points to look into. So that is done by this. The number of points is number of levels is 4, number of heads is 8. So you want another attention layer or attention weight layer to produce. It's also a linear layer that produces this thing to do that. So now once you have those two layers will produce whatever is required, the delta x delta y and the corresponding attention weight. So one thing to look into bit closely is both of these layers, the sampling offset layer and the attention weight layer, are actually operating on a hidden state, which is the input embeddings plus positional embeddings. And so this is similar. Yeah, so they both operate on a hidden state which contains the positional information as well, and the value projection layer operates on a input embeddings. There is no positional embedding information to it. So this is actually similar to what's happening in normal say self attention. So that concept remains the same. And in the end we will have an output projection layer to say it's similar to what's in a normal attention. So the big thing is how the query and key interact is changed. So there is no query projection layer or key projection layer. Instead we have a sampling offset layer and a weight layer. So that is the main difference. And so another thing to note is a big implementation detail is there is something called offset normalizer that normalizes the offset. So this, as we said, we want the delta x delta y and we want it to be in the feature space. So we divide each predicted offset across each feature layer by their corresponding feature map dimension, so that so that they become normalized. So this is what I explained here. So that is one, it's in the paper, in the implementation, the open source implementation have the same thing. And in the end, uh, after that it's the same. Now you have to do a softmax across the attention weights, and then you have to multiply them. So that is what is happening. So as you can see, initially we had this many, uh, this is our attention predicted weight, 8 head, 4 layer, 4 levels. This is the delta x delta y is the same, and then we add them. So we add the sampling points to the reference points. So the reference points, if you remember, was 2 2 3 9 8 0 4 comma 2. And we uh, yeah, so what happens is it will, you will have to do some broadcasting where you will have to squeeze in a dimension, and then this will get broadcasted, and you can add this this here, 23980 comma 4 comma 4 comma 2. So you have to add one 2 dimensions here, so that it will get added here. So what is happening is, for each of the four, each query or each of the reference point across each layer, you get added 4 delta x delta y's across 8 different heads. So in the end you will get this many sampling locations. So this many sampling locations are the keys that we should look into. So that is a bit more clear. Maybe I can explain it once again. So what you have is for 4 2 3 8 9 0 1 comma 4 comma 1 comma 2, and this is the reference, and this is the the second one will be the network predicted delta x across 8 different heads, 4 points per level, and you add them up. What this addition does is, for each level you add 4 delta x delta y's, and you finally get this. So this many sampling locations are there. Now we have to look into this sampling locations. So now we have to do that. So if you so this is the image, as I said. So here, for each query, we have, say, corresponding weights, corresponding sampling locations predicted, for reference point added, then you have to add it, aggregate them, sum it out. Yeah, that's what's happening. So now what we have is, we have to uh, go to the, so this many points, this many locations are there, right? So this many locations are there, and for each query, so we have, for each query we have this many locations to go and attend to. So this many locations to attend to across this many heads. So how that is done is with the help of a function called function.get sample. So the official implementation actually have a CUDA kernel for this, but this is from Hugging Face Transformers, where they have a PyTorch implementation for this as well. So what they do is, initially, now what we have is, uh, so we have the value vector. So what is the value? The value is actually 4 comma 23890 comma 256, right? So we need, so this value is around different features, right? So these features are yeah. So what we have is, now we have this value vector and this many sampling locations. So what we can do is, we have to correspondingly look into all the sampling location across each layer. So what we do is, we initially split the layers. So this is required for the torch dot grid sample to work properly. And yeah, so the head dimension can be moved to here, so it become 32. And then what we do is, we can sample, we can index into each of the levels, which is 4 here, and correspondingly look into each of the split dimension. So what happens is, so the corresponding sampling will become 23 2380 uh, 4 comma 4 comma 2. And now when we index to one of them, so we have four layers, suppose we index to one of them, it become 4 comma 2. And then this many sampling locations across one level, which is say, this is the first level we look into, 134 for 134. So this has to be again rearranged. So this will go here, and this will also go here. So it become 32 8 multiplied by 4, then 32 this permuted to here, and 134 comma 134. So this is actually required for the grid sample to work. And also for the grid sample to work, it should be in -1 1. I will show how that's done. So now once you have this, so what grid sample does is, grid sample will output comma 4, right? So it will do a bilinear interpolation of 4 points. So it will, in this feature map, it will look into, these are xy, right? 4 points, 4 xy points. It will go look into the four. So what happens is, so you have your 134 134. It will look into the four xy points, and for each of these four xy points, it will look into four other points near them, and they will do a bilinear interpolation of all those points and produce 4 points, which contains the information of the all other 4 points. So essentially this will be the output, and this output is for 134 comma 134. Similarly for 67.67 and 34 into 34 and 17 into 17, you will have the similar outputs. And this similar outputs will be finally stacked, and you what you get will be 32 32. This will be like, this will be 1 2. Similarly there will be 3 and 4 for 34 and 17. So 23980 comma 4 comma 4, right? After stacking along, the minus dimension is equal to -2, you will get this output. Now you will rearrange them to batches and heads, and essentially what will this is actually 4 into 8, right? And this will become 16. Okay, maybe I can show the summation first. So you can actually flatten them, and now you will have 32 32 23980. If you flatten them, this will be bigger. Now if you remember, we have a parallel network predicting. So this is the sampled bilinear plus bilinear projection. We get this, and we have a parallel network that predicts us the attention scores of all these 16 points, right? So now we can do a multiplication of these two things, and you will get uh, a vector that is having those multiplied, the weights multiplied, and you sum over the last dimension, and you get this, which this is 4 into 8, this is 32. You bring it here, you bring it here, this become 8 into 32 is 256. It become 256 23980. When you resample, you become 23980 to 56, which is the same dimension as the query dimension, which is what we want out of an attention layer, right? So then this will be passed through a projection layer, which is 256 comma 256. That is the same as the self attention. So what you want to understand is, we end up here by only attending to 16 keys and not all the keys. So that is what this deformable attention is doing. Now if I go to code, this is what is happening. As I said, for sampling grid sample to work, you need to have sampling location in -1 to 1. So that is an like PyTorch specific detail. Then I said you have to split it across the hy spatial dimension, and then for